October 15th, 1943. Deep within the forests of northern Germany, a team of Luftwaffe engineers approached what would become one of the most significant intelligence coups of the European Air War. Sitting on the tarmac at Rechlin, Germany's premier aviation testing facility, was a pristine example of American engineering power that had dominated the skies over occupied Europe for months. The Republic P-47 Thunderbolt, freshly painted with German markings, was about to reveal secrets that would fundamentally alter how Nazi Germany understood their enemy's true industrial capabilities. What these engineers discovered when they systematically dismantled this captured American fighter would send shockwaves through the highest levels of German command. The findings were so profound, so disturbing to Nazi leadership, that they challenged every assumption Germany had made about American manufacturing capacity and technological sophistication. This wasn't just another enemy aircraft to be studied and countered. This was physical evidence of an industrial machine operating at a scale that German engineers had never imagined possible. The story begins with a routine escort mission gone wrong, when mechanical failure forced an American pilot to make a fateful decision that would gift the Luftwaffe an intelligence treasure beyond their wildest dreams. But what started as German good fortune would quickly transform into a nightmare revelation about the true nature of their adversary. For months, German pilots had been encountering these massive American fighters over the battlefields of Western Europe, dismissing them as clumsy, oversized machines that posed little threat to experienced Luftwaffe aces. They called them flying bathtubs, mocking their ungainly appearance and sluggish performance at the medium altitudes where most aerial combat occurred. German combat reports consistently noted how easily their nimble Messerschmitt and Focke-Wulf fighters could outmaneuver the lumbering American giants in traditional dogfighting scenarios. Yet disturbing patterns had begun emerging from these same combat reports. Pilots described Thunderbolts that refused to die, absorbing punishment that would have destroyed any German fighter 3 times over. They reported American aircraft that could simply disappear in high-speed dives, accelerating to velocities no German fighter could match. Most troubling of all were the accounts of devastating firepower from synchronized machine guns that could literally disintegrate enemy aircraft in seconds of concentrated fire. These contradictions demanded explanation, and the intact Thunderbolt at Rechlin promised to provide answers. The aircraft had arrived through circumstances that could only be described as providential from the German perspective. Second Lieutenant William Roach, flying escort duty over occupied France, had encountered fuel starvation that forced an emergency landing at what he mistook for a friendly airfield. His perfectly preserved P-47, complete with full ammunition load and operational systems, represented an intelligence windfall that German technical services could barely have dared to hope for. The initial examination team approached their task with professional skepticism, tempered by growing unease. These were seasoned aviation engineers who had evaluated captured British Spitfires and Soviet fighters without particular concern. German aircraft technology was widely recognized as the most advanced in the world, and previous examinations of enemy equipment had generally confirmed German technical superiority. The Thunderbolt, however, would prove different in ways that challenged fundamental assumptions about American industrial capabilities. Hans Werner Lerche, Germany's premier test pilot and chief evaluation engineer, drew the assignment to conduct the first comprehensive flight assessment. Lerche possessed an almost supernatural ability to extract performance secrets from unfamiliar aircraft, having successfully evaluated over 100 different types without ever suffering a serious accident. His methodical approach to flight testing had revealed the tactical vulnerabilities of every Allied fighter that had fallen into German hands. Yet approaching the Thunderbolt's cockpit for the first time, even Lerche felt intimidated by the complexity confronting him. The instrument panel contained nearly twice the number of gauges found in contemporary German fighters, Strange levers controlled systems he had never encountered in German designs. Most perplexing was an elaborate network of controls managing something called a turbo supercharger, a technology that German engineers understood theoretically but had never successfully implemented in production aircraft. The engine itself presented the first major shock to German preconceptions. The Pratt & Whitney R2800 double wasp was unlike anything in German service, featuring 18 cylinders arranged in 2 rows around a massive crankshaft. Total displacement exceeded 46 litres, dwarfing even Germany's largest radial engines. But displacement alone didn't explain the significant power advantage this American engine demonstrated over German equivalents. What truly astounded the evaluation team was the quality of materials and manufacturing precision evident throughout every component. The crankshaft was forged from the steel alloys that German metallurgists examined with professional envy, recognizing materials they could no longer obtain in sufficient quantities due to strategic shortages. The pistons incorporated sodium-cooled valves designed to handle extreme temperatures, while the fuel injection system operated with precision that German engineers associated with laboratory equipment rather than combat aircraft expected to function reliably under harsh battlefield conditions. Most telling was the complete absence of material substitutions or quality compromises that had become standard practice in German wartime production. Every component appeared to be manufactured exactly as originally designed, using all specified materials without the desperate improvisations that increasingly characterized late-war German manufacturing as strategic bombing degraded industrial capacity. The turbo supercharger system revealed engineering sophistication that Germany had attempted to develop but never successfully implemented in mass production. Exhaust gases from all 18 cylinders were collected through insulated manifolds and routed along the fuselage to a turbine unit that drove a centrifugal compressor, forcing additional air into the engine's intake system. The entire installation included intercoolers, automatic pressure regulators, and precision control mechanisms that functioned flawlessly without requiring constant pilot intervention. German engineers understood these principles perfectly and had conducted experimental programs exploring similar approaches. But implementing such systems in combat aircraft had proven impossible given material shortages and manufacturing limitations that plagued German industry. The Americans had not only solved all technical challenges but had installed the complete system as standard equipment on every Thunderbolt produced. This casual implementation of advanced technology as routine production equipment revealed industrial capacity that German engineers found genuinely incomprehensible. The armament installation provided another lesson in American abundance and systematic engineering excellence. 8 Browning machine guns were mounted in the wings, each fed from individual ammunition boxes containing over 400 rounds. Total ammunition capacity exceeded 3,000 rounds across all weapons, allowing sustained fire for nearly 30 seconds at combined rates approaching 100 rounds per second. When properly harmonized, this volume of fire created zones of destruction that no aircraft could survive. But beyond the impressive specifications lay evidence of manufacturing quality that exceeded German standards, even in peacetime production. Each gun was mounted in electrically heated compartments to prevent freezing at high altitude. Spent cartridge cases were collected through elaborate chute systems that prevented interference with aircraft control surfaces. The installation functioned flawlessly during extensive German testing, firing thousands of rounds under varying atmospheric conditions with no malfunctions recorded. What emerged from these initial examinations was a disturbing pattern that would only become more pronounced as the evaluation progressed. The Thunderbolt represented not just an advanced aircraft design, but physical evidence of an industrial philosophy that prioritized absolute capability over elegant efficiency, abundant resources over careful optimization, and systematic material advantage over individual technical excellence. The implications were beginning to dawn on German technical staff with uncomfortable clarity. They were not examining the product of a desperate nation struggling to match German technological superiority. They were studying the routine output of an industrial machine operating at scales that made German production capacity appear almost primitive by comparison. The full scope of German shock would only become apparent when engineers began examining the Thunderbolt's protective systems. German fighters typically carried minimal armor to preserve performance characteristics, accepting higher pilot casualties as an inevitable cost of maintaining competitive speed and maneuverability. The American approach represented a fundamentally different philosophy that prioritized pilot survival even at significant weight penalties. The cockpit armor alone weighed over 200 pounds, equivalent to mounting 2 additional machine guns with full ammunition loads. Heavy steel plates surrounded the pilot from multiple angles, creating what American designers called an armored bathtub that could stop machine gun rounds and resist cannon shell fragments. The windscreen incorporated bulletproof glass, nearly 2 inches thick, while additional armor protected critical systems, including oil coolers and the vulnerable turbo supercharger installation. This commitment to protection extended throughout the aircraft in ways that revealed American willingness to accept performance compromises that German doctrine considered unacceptable. Every vital component showed evidence of redundant protection or backup systems designed to keep the aircraft flying despite battle damage. The hydraulic system included multiple independent circuits that could function even if primary lines were severed. Control cables were duplicated throughout the airframe with automatic switching mechanisms that engaged if primary cables failed. German engineers conducting stress testing discovered that the wing spars could support loads 3 times the aircraft's maximum weight, representing engineering margins that seemed almost wasteful from German perspectives shaped by resource constraints. The entire airframe demonstrated structural integrity that exceeded anything in German service, built to withstand punishment that would reduce conventional fighters to scattered debris. The radio installation provided yet another revelation of American technological superiority. The aircraft carried multiple communication systems operating with clarity and range that exceeded contemporary German equivalents. German radio equipment suffered from persistent interference problems that American engineers had apparently solved through superior component design and advanced shielding techniques. Most sophisticated was an identification system that automatically distinguished friendly from enemy aircraft, preventing the friendly fire incidents that plagued German formations operating in increasingly chaotic battlefield conditions. This level of automated identification represented technological sophistication that German forces completely lacked in operational service. But perhaps the most disturbing discovery came not from any individual advanced system, but from the cumulative impression of quality and completeness that characterized every aspect of the aircraft. Nothing appeared compromised due to material shortages. Nothing showed evidence of substitute materials being used because preferred components were unavailable. Nothing reflected the desperate improvisations that had become standard practice in German production as strategic bombing campaigns degraded industrial capacity. The Thunderbolt had been manufactured exactly as American designers intended, using all specified materials and processes without apparent compromises forced by resource limitations. This level of manufacturing fidelity to original design specifications was becoming increasingly impossible for German industry to achieve as the war progressed and critical materials became scarce. Flight testing revealed performance characteristics that contradicted every assumption German pilots had developed about American fighter capabilities. Below 15,000 feet, the Thunderbolt performed exactly as German combat reports described, appearing sluggish and outmaneuvered by contemporary German fighters in traditional turning engagements. But above 20,000 feet, the aircraft transformed into something entirely different. The turbo supercharger system, functioning with increasing efficiency as atmospheric pressure decreased, maintained full engine power at altitudes where German fighters gasped for oxygen and lost performance dramatically. At 30,000 feet, where American bomber formations operated and where aerial combat increasingly occurred, the Thunderbolt demonstrated clear superiority over every German fighter in service. Hans Werner Lercher documented maximum speeds that exceeded German capabilities by significant margins at combat altitudes. While German fighters struggled to maintain 370 miles per hour at 30,000 feet, the Thunderbolt achieved over 120 miles per hour at the same altitude, creating tactical advantages that German pilots were powerless to counter. The dive performance proved even more devastating to German tactical assumptions. Once the Thunderbolt entered a steep descent, it accelerated to velocities approaching the sound barrier, reaching speeds where no German fighter could follow without encountering compressibility effects that rendered their controls ineffective. American pilots in trouble could simply roll inverted and dive away at velocities that made pursuit impossible. Range capabilities with external fuel tanks revealed another dimension of American strategic thinking that German planners had failed to anticipate. Early Thunderbolt models had possessed limited operational radius that restricted their effectiveness to short-range missions near friendly bases. But by late 1943, modified variants equipped with drop tanks could escort bomber formations deep into German territory, providing protective coverage that extended hundreds of miles beyond what German planning had considered possible. This evolution in American fighter capabilities represented systematic engineering improvement applied to operational requirements, demonstrating an industrial system capable of identifying problems and implementing solutions with remarkable speed. German aircraft development, constrained by material shortages and manufacturing limitations, could barely maintain existing production standards, much less implement major design improvements. The psychological impact on German technical staff conducting these evaluations proved as significant as the technical revelations themselves. These were professional engineers who had spent careers developing what they considered the world's most advanced aviation technology. The Thunderbolt forced them to confront uncomfortable truths about American industrial capacity that challenged fundamental assumptions about German technological superiority. Intelligence reports compiled at Rechlin and distributed throughout Luftwaffe technical services emphasized the disturbing implications of what they had discovered. The Americans were not struggling to match German engineering excellence through desperate improvisation and inferior substitutes. They were systematically exceeding German capabilities through superior resources applied with methodical efficiency. Every captured Thunderbolt told the same story of American abundance translated into overwhelming material advantage. The aircraft represented routine production output from factories operating at scales that made German industrial capacity appear almost primitive. Individual American plants frequently exceeded the total output of entire German industrial regions, while maintaining quality standards that German facilities could no longer achieve under wartime conditions. The broader strategic implications became increasingly clear as additional Thunderbolts fell into German hands and underwent similar evaluation procedures. These were not isolated examples of American technical achievement, but representative samples of mass production systems that could manufacture thousands of such aircraft while simultaneously producing everything else a modern military required. German engineers found themselves documenting capabilities they understood perfectly but could never replicate given their nation's deteriorating industrial situation. Knowledge of American techniques provided no practical benefit when Germany lacked the aluminum, steel, skilled labor, undamaged factories, and functioning transportation networks necessary to implement equivalent production methods. The evaluation program continued through the winter months as more captured American aircraft arrived at Rechlin for systematic analysis. Each examination confirmed the same fundamental pattern of American technological and industrial superiority applied at national scale. The lessons were professionally documented and accurately reported through German command structures, but the knowledge arrived far too late to influence strategic outcomes that had already been determined by industrial mathematics beyond German capacity to alter. The captured Thunderbolts underwent increasingly detailed analysis as German engineers began stripping away layers of American engineering philosophy that had remained hidden beneath initial surface examinations. What they discovered in the aircraft's maintenance systems revealed an industrial mindset that prioritized operational efficiency over production economy, a luxury that German designers could barely comprehend given their resource constraints. Every major component could be accessed through large panels secured with quick-release fasteners, requiring only basic tools. The massive radial engine could be completely removed and replaced in field conditions within hours using standard lifting equipment. German fighters designed with the expectation of factory-level maintenance for major repairs typically required extensive disassembly that could ground aircraft for weeks when critical components failed. This difference reflected fundamental philosophical approaches to aviation design. American engineers had apparently dedicated substantial resources to ensuring that combat aircraft could be maintained by mechanics working in forward air bases under adverse conditions. They had solved problems that German designers considered secondary concerns, creating systems that functioned reliably even when serviced by personnel with limited specialized training. The engine management systems provided another revelation of American technological sophistication applied to practical operational requirements. German pilots manually controlled engine parameters through constant throttle and mixture adjustments, requiring continuous attention that diverted focus from combat situations. The Thunderbolt featured automatic systems that managed fuel flow, ignition, timing, and supercharger boost without pilot intervention beyond setting desired power levels. These automated controls weren't experimental equipment reserved for special applications. They represented standard production features installed in every aircraft that rolled off American assembly lines. The casual implementation of such advanced technology demonstrated manufacturing confidence that German engineers found almost incomprehensible given their own struggles with basic component reliability. The fuel system architecture revealed American abundance translated into engineering redundancy. Multiple fuel tanks were connected through sophisticated pumping systems that automatically maintained proper weight distribution as fuel was consumed. Emergency systems could transfer fuel between tanks if primary pumps failed, while backup electrical systems ensured continued operation even if main power sources were damaged. German fighters typically featured simpler fuel arrangements with minimal backup systems, accepting higher risks of fuel starvation if primary components failed. The American approach represented willingness to accept weight and complexity penalties in exchange for operational reliability, a trade-off that German resource constraints made increasingly impossible to implement. The hydraulic systems demonstrated similar philosophical differences between American and German design approaches. The Thunderbolt featured multiple independent hydraulic circuits that could operate landing gear, flaps, and gun charging mechanisms, even if primary systems sustained battle damage. Backup manual systems provided final redundancy if all hydraulic power failed. This level of systematic redundancy appeared throughout every aircraft system, creating what German engineers recognized as defensive design philosophy that assumed components would fail under combat stress. American designers had apparently engineered solutions for failure modes that German engineers considered acceptable risks, demonstrating industrial capacity that could afford to solve problems beyond basic operational requirements. The ammunition feed systems provided particularly impressive examples of American engineering attention to detail. Each machine gun featured individual electric motors that powered ammunition belts through complex paths within the wing structure. These systems prevented jamming during high-stress maneuvering that could disrupt gravity-fed mechanisms used in German designs. The ammunition itself revealed another dimension of American industrial superiority. Every cartridge was manufactured to tolerances measured in thousandths of inches, ensuring reliable feeding through synchronized gun mechanisms operating at tremendous rates of fire. German ammunition production, struggling with material shortages and quality control problems, could no longer achieve such consistent specifications. The electrical systems demonstrated American willingness to incorporate advanced technology as standard equipment rather than specialized additions. The aircraft featured multiple generators providing redundant power sources, while sophisticated voltage regulation systems maintained consistent electrical supply under varying engine speeds and combat loads. Most impressive was the integration of electrical heating systems throughout critical components. Gun bays were heated to prevent freezing at high altitude, where temperatures could drop to 60 degrees below zero. Pitot tubes and instrument lines featured electrical heating that prevented ice formation that could disable flight instruments during combat operations. German aircraft typically relied on engine heat and cabin air circulation for anti-icing protection, accepting reduced effectiveness at extreme altitudes rather than installing dedicated electrical systems. The American approach represented systematic engineering solutions for environmental challenges that German designers considered manageable through operational limitations. The oxygen systems revealed another area where American engineers had solved problems that German aviation medicine considered acceptable compromises. The Thunderbolt featured high-pressure oxygen supplies with automatic regulators that adjusted flow rates based on altitude without requiring pilot attention. German pilots manually controlled oxygen flow through mechanical regulators, creating opportunities for hypoxia if proper procedures weren't followed during combat stress. The American system eliminated human error factors through automated controls that functioned reliably even if pilots became unconscious or disoriented during high-altitude operations. The cockpit layout itself demonstrated American attention to pilot efficiency under combat conditions. Every control was positioned within easy reach of a properly strapped pilot, while emergency systems featured distinctive shapes and colors that could be identified by touch during night operations or when visual attention was focused outside the aircraft. German cockpit designs typically prioritized compact arrangements that minimized aircraft dimensions, sometimes requiring pilots to reach awkwardly for critical controls. The American approach accepted larger cockpit volumes in exchange for optimized pilot workload, demonstrating willingness to sacrifice theoretical performance for practical operational advantages. The structural engineering revealed American confidence in their materials science capabilities. Wing spars were manufactured from aluminum alloys that German metallurgists examined with professional admiration, recognizing compositions they could no longer produce due to strategic material shortages. The manufacturing quality was consistently superior throughout every component examined. Surface finishes were smooth and uniform, indicating precision tooling and quality control systems that German production facilities could barely maintain under wartime conditions. Even secondary components showed evidence of careful manufacturing that exceeded German standards for primary structural elements. The landing gear systems demonstrated American engineering philosophy applied to seemingly routine mechanisms. The retraction systems featured multiple backup methods, ensuring gear extension even if primary hydraulic power failed completely. Emergency manual systems could lower landing gear through purely mechanical linkages that required no external power sources. German landing gear designs typically accepted higher risks of gear failure, rather than incorporating extensive backup systems that added weight and complexity. The American approach represented systematic engineering for worst-case scenarios, demonstrating industrial capacity that could afford to solve problems beyond minimum operational requirements. The propeller installation revealed another area of American technological superiority. The Hamilton Standard propeller featured automatic pitch control that optimized blade angles for varying flight conditions without pilot intervention. The system included governors that prevented overspeeding and automatic feathering mechanisms that reduced drag if engine failure occurred. German propeller designs typically required manual pitch adjustment or featured simpler automatic systems with limited capability ranges. The American installation demonstrated sophisticated control technology applied to routine aircraft components, indicating systematic technological advancement across all system categories. As winter deepened and evaluation programs continued, German engineers began documenting performance characteristics that fundamentally challenged Luftwaffe tactical doctrine. The data revealed that above 25,000 feet, where combat increasingly occurred as American bomber formations flew higher to escape German anti-aircraft fire, the Thunderbolt possessed decisive advantages over every German fighter in service. The service ceiling comparisons proved particularly discouraging for German tactical planners. The Thunderbolt could operate effectively at altitudes exceeding 40,000 feet, while German fighters rarely functioned well above 35,000 feet. This altitude advantage meant American escorts could choose engagement conditions that maximized their technological superiority while minimizing German tactical advantages. The dive performance data contradicted every assumption German pilots had developed about engaging Thunderbolts in combat. Once the American fighter entered a steep descent, it could achieve velocities approaching 500 miles per hour, speeds that no German fighter could match without encountering compressibility effects that rendered controls ineffective. Range calculations with external fuel tanks revealed strategic implications that German planners had failed to anticipate. Modified Thunderbolts could escort bomber formations on missions penetrating deep into German territory, providing protective coverage that extended operational ranges by hundreds of miles beyond what German intelligence had considered possible. These extended range capabilities meant that American fighters could engage German interceptors at times and places of their choosing, while German fighters were increasingly forced into defensive reactions. The strategic initiative was shifting decisively toward American forces equipped with aircraft that could operate beyond German tactical response capabilities. The psychological impact on German evaluation teams proved as significant as the technical discoveries themselves. These were experienced aviation professionals who had spent careers developing what they considered the world's most advanced military aircraft. The Thunderbolt evaluations forced them to confront uncomfortable truths about American industrial capabilities that challenged fundamental assumptions about German technological leadership. Intelligence summaries compiled at Rechlin documented systematic American advantages across every category of aircraft performance and manufacturing quality. The reports emphasized that these advantages were not isolated examples of American technical achievement, but representative samples of mass production systems operating at scales that exceeded total German industrial capacity. The evaluation data revealed that American aircraft production was not struggling to match German quality through desperate improvisation and inferior substitutes. American factories were systematically exceeding German capabilities through superior resources applied with methodical engineering discipline, creating weapons systems that outclassed German equivalents in aggregate performance, even when German designs showed advantages in specific isolated parameters. The captured Thunderbolts provided German engineers with detailed knowledge of American capabilities, but this knowledge arrived too late to influence strategic outcomes that had already been determined by industrial mathematics beyond German capacity to alter. Understanding American technological superiority could not provide Germany with the resources necessary to compete effectively against opponents whose combined industrial capacity exceeded German production by factors of 5 or more. The lessons learned from systematic evaluation of captured American aircraft would prove academically interesting, but strategically irrelevant, as Germany lacked the aluminum, steel, skilled labour, undamaged factories, and functioning transportation networks necessary to implement equivalent production methods. Knowledge without resources remained powerless to change the fundamental trajectory of industrial warfare that had already determined the conflict's inevitable conclusion. The most profound revelation emerged when German engineers began examining the Thunderbolt's production markings and component serial numbers. Every part bore evidence of a manufacturing system operating with precision that exceeded German peacetime standards, yet these aircraft were being produced during the most intensive period of American wartime expansion. Quality control stamps revealed inspection procedures that German factories could barely maintain under ideal conditions, implemented routinely across thousands of aircraft rolling off American assembly lines monthly. The wing construction alone demonstrated manufacturing capabilities that challenged German understanding of industrial possibility. Each wing section was assembled from hundreds of precisely machined components, fitted together with tolerances measured in thousandths of inches. German engineers discovered that American factories were achieving structural precision that their own facilities considered achievable only through hand-fitting by master craftsmen. Yet these wings were being mass-produced by workers who had learned their trades in weeks rather than years. The riveting patterns throughout the airframe showed systematic quality that German production supervisors found genuinely astounding. Every rivet was perfectly formed, correctly tensioned, and positioned with mathematical precision. There were no signs of the hasty workmanship that had crept into German production, as skilled workers were drafted for military service and replaced with barely trained personnel. The Americans had somehow maintained manufacturing excellence while expanding production to scales that German industry had never approached. Component dating revealed the most disturbing truth of all. This particular Thunderbolt had been manufactured in September 1943, during the peak of American industrial mobilization, when factories were supposedly struggling to meet impossible production quotas. Yet every system functioned flawlessly, every component met design specifications perfectly, and the overall quality exceeded what German engineers expected from prototype aircraft built under laboratory conditions. The engine manufacturing data proved particularly troubling for German technical analysts. The Pratt & Whitney plant records, partially visible on component tags, indicated that this specific engine was one of over 800 produced that month at a single facility. German engineers calculated that this represented more high-performance aircraft engines than their entire industry could manufacture in 6 months. Produced by one American factory in 30 days while maintaining quality standards that German facilities struggled to achieve in limited production runs. The aluminum quality throughout the airframe revealed another dimension of American industrial superiority that German metallurgists found deeply concerning. Every sheet, every extrusion, every forged component showed evidence of consistent alloy composition and heat treatment that indicated raw material supplies of unlimited quantity and unwavering quality. German aluminum production, hampered by bauxite shortages and power restrictions, could no longer achieve such material consistency even for priority aircraft programs. The strategic implications became increasingly clear as German engineers compiled their technical reports. They were not examining evidence of American desperation or hasty improvisation. They were studying the routine output of an industrial machine that had solved problems German engineers considered impossible under wartime conditions, implementing solutions with casual efficiency that suggested vast reserves of capability held in reserve. The manufacturing techniques evident throughout the aircraft demonstrated systematic approaches to quantity production that German industry had never successfully implemented. American factories had apparently developed assembly methods that maintained precision while achieving production rates that exceeded German theoretical calculations of industrial possibility. The evidence suggested manufacturing systems operating at efficiency levels that made German production appear primitive by comparison. The quality of secondary components proved as revealing as major systems. Screws, bolts, washers, and gaskets all showed evidence of precision manufacturing and material quality that German suppliers could no longer provide consistently. Even the smallest components were manufactured to specifications that exceeded German standards for primary structural elements, indicating industrial capacity that could afford excellence in details that German resource constraints forced engineers to consider acceptable compromises. The electrical wiring throughout the aircraft demonstrated another area where American industrial capability exceeded German understanding. Every wire was precisely cut to length, properly insulated with materials that German electrical suppliers could no longer obtain, and routed through the airframe with systematic organization that reflected engineering attention to maintenance accessibility. German aircraft wiring, increasingly improvised with substitute materials, looked crude by comparison. The paint and finishing systems revealed American attention to details that German production schedules no longer permitted. Multiple primer coats, precisely applied color schemes, and protective finishes that would resist corrosion in harsh operational environments. German aircraft were increasingly delivered with minimal finish work as production priorities focused on quantity over appearance, yet the Americans had maintained finishing standards that exceeded German peacetime practices. Component packaging and protection during assembly showed systematic approaches to quality preservation that German factories had abandoned as production pressures increased. Every sensitive component was wrapped, sealed, and protected during installation with procedures that prevented contamination or damage. The Americans had maintained assembly practices that German production supervisors considered luxuries they could no longer afford. The tooling marks visible on machine surfaces throughout the aircraft indicated manufacturing equipment of superior precision, compare quality, and to German machine tools. American factories were apparently using cutting tools and forming equipment that produced surface finishes German manufacturers associated with specialized prototype work, yet these finishes appeared on every component of mass-produced combat aircraft. The captured Thunderbolt had revealed its final secret to the stunned German engineers at Rechlin. This wasn't just superior technology or advanced engineering. This was evidence of an industrial colossus operating at scales that rendered German production capacity almost medieval by comparison. Every rivet, every component, every system spoke to manufacturing capabilities that German industry could never hope to match, even under peacetime conditions. The intelligence reports compiled from months of systematic analysis would circulate through Luftwaffe headquarters, documenting with clinical precision the dimensions of Germany's industrial defeat. German engineers had learned everything they needed to know about American fighter technology. They understood the turbo supercharger systems, the automated engine controls, the redundant safety systems, and the manufacturing processes that created such remarkable aircraft. But knowledge without resources remained powerless to change anything. The war's outcome had never depended on tactical brilliance or pilot courage. Though Germany possessed both in abundance, it had been determined by industrial mathematics that reduced combat to simple arithmetic. America could design adequate aircraft and produce them in quantities that made German qualitative advantages strategically irrelevant. They could afford to over-engineer every system, overbuild every component, and oversupply every squadron, while simultaneously producing everything else a modern war required. The captured Thunderbolt would eventually be recovered by advancing Allied forces in May 1945, found among dozens of other captured aircraft that represented Germany's desperate attempt to understand an enemy they could observe but never hope to equal. The pristine American fighter, still wearing its hastily applied German markings, stood as a monument to industrial warfare's fundamental truth. In the end, the Germans had taken apart more than just a captured aircraft. They had dissected their own defeat, examining piece by piece the evidence of America's overwhelming material superiority. The Thunderbolt had taught them everything they needed to know about why they were losing the war. The lesson had arrived with perfect clarity, documented with German precision, and delivered far too late to matter. The arsenal of democracy had spoken, and the sky belonged to America,